Now, this is quite a story from NASA because for the second time in history, a man-made object has left our solar system.
Voyager 2 detected a fiery plasma wall in the heliopause, where the sun's outward-blowing solar winds clash with cosmic rays. This barrier protects the solar system by repulsing and weakening cosmic rays.
Voyager 2, launched by NASA in 1977, has been journeying through the cosmos for nearly 5 decades. Designed originally for a 4-year mission to explore the outer planets, the spacecraft has long surpassed its intended purpose. In 2018, it became the second human-made object to enter interstellar space, a region beyond the influence of the sun's solar wind. As it traveled farther from the sun than any spacecraft save its twin, Voyager 1, the probe began sending back data from a frontier that had never been directly explored. But just recently, it did something no one expected. It made a discovery that defied existing theories about the outer limits of our solar system. Before we start, smash the like and subscribe buttons for more updates. At a distance of over 12 billion miles from Earth, Voyager 2 transmitted data that revealed a bizarre and unexplainable phenomenon. Scientists had long believed that the heliopause, the boundary where the sun's solar wind meets the interstellar medium, acted like a relatively clean and sharp divider. This was supposed to be the point at which the solar wind, streaming outward from the sun, slows down and is overcome by the pressure of particles from interstellar space. When Voyager 1 crossed it in 2012, it confirmed the heliopause's existence and provided valuable data. But Voyager 2's recent readings showed something else entirely. It encountered a region where the plasma density had suddenly spiked to levels far beyond what had been predicted, and in a way that didn't align with any known models of heliospheric behavior. The shocking part wasn't just the density spike, it was the nature of the particles themselves. Voyager 2 detected energetic particles that behaved unlike any observed before, fluctuating in a way that indicated an oscillating boundary. Instead of a fixed line where solar influence ends and interstellar influence begins, Voyager 2 appeared to be dancing in and out of an undefined transitional zone. This zone pulsed with energy, fluctuated in density, and echoed with mysterious low-frequency waves that seemed to resonate from deep space. Even more intriguing, Voyager 2 recorded magnetic field reversals that didn't correspond to solar activity. For decades, scientists had assumed that magnetic field variations near the heliopause would be relatively uniform and would weaken consistently with distance. But the reversals Voyager 2 witnessed weren't just anomalies, they were patterns, rhythmic and recurring, as though some unknown force or structure was influencing space at the edge of the heliosphere. This raised the possibility of completely new mechanisms at play in interstellar interaction, mechanisms that no solar or astrophysical models currently accounted for. The implications of this are staggering. If the heliopause is not a clean boundary, but rather a thick, undulating active region, then the entire model of how our solar system interacts with interstellar space must be reconsidered. The idea that our solar system is cocooned in a bubble of solar wind, a protective shield against cosmic radiation, has underpinned decades of research. Voyager 2's data suggests that this bubble is not just porous, but possibly alive with interaction. Particles from interstellar space may be penetrating deeper into our solar system than once thought, and conversely, solar particles may be escaping in more complex patterns. There's also a possibility that this discovery hints at the existence of previously unknown interstellar structures. If space at the edge of the solar system is behaving like a dynamic membrane rather than a static shell, it could mean that the interstellar medium itself is far more structured and turbulent than believed. It might contain magnetic filaments, eddies of plasma, or even directional flows of energy that influence star systems at their borders. Voyager 2 could be detecting the fingerprints of galactic-scale phenomena, compressing or shaping the outer solar system in subtle but persistent ways. The potential for such structures opens a whole new arena for exploration. Scientists have long considered the interstellar medium to be a mostly uniform, sparse collection of particles, gas, and dust. But Voyager 2's detection of such intense variability suggests that the edge of the solar system is not entering a void, but a dynamic and possibly hostile environment. This might change how future deep space missions are planned. Spacecraft traveling beyond the heliosphere may have to account for unforeseen particle radiation, fluctuating magnetic fields, and energetic plasma storms that could affect their instruments or trajectories. Another layer of this mystery involves the unexpected heating of particles in this boundary zone. Voyager 2's instruments measured temperatures that should not be possible given the known energy inputs in that region. Particles were not only denser, but they were hotter, seemingly energized by an invisible process. This raises questions about how energy is transferred in interstellar space. Could there be unknown wave-particle interactions occurring? Could this be the result of magnetic reconnection events, where interstellar and solar magnetic fields collide and explosively rearrange? Or is there something even more exotic at play, phenomena that hint at physics beyond the current standard models? There's also the tantalizing possibility that this discovery brushes against one of the greatest open questions in astrophysics: dark matter and dark energy. Although Voyager 2 is not equipped to detect either directly, the strange dynamics at the heliopause might provide indirect clues. Some theories suggest that dark matter could subtly influence the distribution and motion of particles at interstellar boundaries. If dark matter is more interactive in localized regions, Voyager 2 might be drifting through one such pocket, its instruments catching the ghostly echoes of invisible mass. Additionally, the low-frequency electromagnetic waves recorded by Voyager 2 have stirred interest. These waves aren't the kind typically associated with solar or planetary activity. Instead, they bear a resemblance to the types of plasma waves theorized to exist in the space between stars. These waves could act like beacons, carrying information across light years. If confirmed, they might represent a natural galactic communication network, a way for cosmic phenomena to propagate changes in magnetic or gravitational conditions across vast distances. Voyager the 2nd of May have stumbled into one such network, passively listening to the ancient chorus of the galaxy. For decades, the edge of the solar system was imagined as a final curtain, the last act in the sun's domain before true emptiness. Voyager 2 has shown that this curtain is not only still rising, but possibly part of a vast, complex interplay of forces we are only beginning to perceive. Its instruments, operating long past their intended lifespan, have become the senses of a civilization reaching into the unknown. The spacecraft is not merely reporting data, it is revealing a new frontier where solar and galactic realms blur and intertwine. Another important implication stems from the comparative data between Voyager 1 and Voyager 2. While both probes crossed the heliopause, they did so at different locations and times. Yet only Voyager 2 encountered this chaotic wave-ridden region. This discrepancy suggests that the heliopause might be asymmetrical or affected by local interstellar conditions, much like weather patterns in Earth's atmosphere. The idea that space weather exists on such a scale challenges previous assumptions about the uniformity of galactic environments. It implies that every star's heliosphere could have its own unique shape, boundary dynamics, and points of vulnerability. Understanding these differences is crucial not just for astronomy, but for the future of human space exploration. As plans to send robotic explorers, or even humans, beyond the boundaries of the solar system develop, knowing what lies ahead becomes a matter of safety and design. Radiation shielding, energy generation, and communication systems all depend on predictions about the surrounding environment. Voyager 2's impossible discovery might be the first real warning that we don't know nearly enough about what lies beyond the sun's reach. One more layer of implication involves cosmic rays. These high-energy particles come from distant sources, such as supernovae or black holes, and are usually deflected by the solar wind and the heliospheric magnetic field. Voyager 2's unexpected findings suggest that the shielding effect at the heliopause may be far less reliable than previously thought. If the heliosphere fluctuates, bends, or even tears at certain points, cosmic rays could slip through and enter the inner solar system with greater frequency. This could affect not only future missions, but also Earth itself, with possible consequences for atmospheric chemistry and long-term climate models. Even our understanding of the solar system's motion through the galaxy comes under scrutiny. As the Sun orbits the galactic center, it moves through different regions of interstellar space, which may contain denser clouds of gas or fields of charged particles. Voyager 2 might be encountering the beginning of such a region, a galactic eddy that interacts with the heliosphere in unexpected ways. This could mean that the edge of the solar system is not a fixed concept, but one that changes depending on our 'our location in the galaxy. The border, in this sense, becomes a living frontier. As the Sun orbits the galactic center, it moves through different regions of interstellar space, which may contain denser clouds of gas or fields of charged particles. Voyager 2 might be encountering the beginning of such a region, a galactic eddy that interacts with the heliosphere in unexpected ways. This could mean that the edge of the solar system is not a fixed concept, but one that changes depending on our location in the galaxy. one that ebbs and flows, breaths and reacts, much like the ocean's tide against a ship's hull. Voyager 2's continued mission now holds a dual role. It is both a sentinel and a scout. It observes the cosmic seas as they are and sends back news of what lies beyond. Every data packet it transmits is a glimpse into an unseen realm, and every deviation from expectation opens new questions. It's a humbling reminder of how little we know about the very space that surrounds our cosmic neighborhood. The idea that a 1970 S-era spacecraft, with less computing power than a modern digital watch, could uncover phenomena that challenge 21st century astrophysics is a testament to the enduring power of exploration. Its discovery pushes the boundary of not just the solar system, but of human understanding. Theories will evolve, models will adapt, and new missions will be envisioned, all because Voyager 2 passed silently into the darkness and found that the darkness was not empty. Instead, it was alive with activity, mystery, and possibility. The spacecraft has revealed that the universe is not content to remain static or passive at its edges. Even at the threshold of our solar domain, space is an arena of surprise. This discovery may also reframe how scientists approach the search for life in the universe. If interstellar space can have structured magnetic fields, dynamic plasma regions, and energy transfer mechanisms, then the notion of habitability might expand. Astrobiology has traditionally focused on planets, moons, and atmospheres, but now attention might shift to how the interstellar environment itself could influence the development of life, especially around stars with different heliospheric conditions. Perhaps life isn't just shaped by its planet, but by the galactic currents flowing through its star's protective bubble. Voyager 2's impossible discovery is far more than an unexpected set of numbers. It's a signal, an announcement that the edge of the solar system is not an ending, but a beginning. It reminds us that while humanity has sent probes to the moon, to Mars, to Jupiter, and beyond, the true frontier may not be a planet at all. It may be the very fabric of space itself, the place where solar winds fall silent and the galaxy begins to whisper. And so Voyager 2 continues, silent but for its pulse of data across the void. It carries no eyes, no ears, no voice, yet it speaks. It speaks of a boundary more wondrous than a line between spheres of influence. It speaks of a universe with more texture, more complexity, and more drama than we ever imagined. Its journey is far from over, and its revelations may be only just beginning. Beyond the dazzling revelation at the heliopause, Voyager 2's discovery continues to reverberate through the scientific community, not simply because it contradicts previous assumptions, but because it opens entirely new dimensions of inquiry. The edge of the solar system, once treated as a static and terminal boundary, has emerged as an evolving region full of dynamics still poorly understood. With each passing moment, Voyager 2 journeys deeper into the interstellar medium, and what it has begun to uncover in the aftermath of that anomalous boundary zone goes far beyond a simple fluctuation in plasma density or magnetic field behavior. What lies beyond the known isn't just unexplored, it might be governed by rules that have not yet been imagined. As Voyager 2 continues its path outward, one of the more immediate questions that arises is, what is the true nature of the interstellar medium itself? Most models have painted it as a sparse, nearly empty void, composed of low-density hydrogen, helium, and trace amounts of other ions and cosmic dust. However, the probe's extended observations following its transition through the heliopause suggest otherwise. It has recorded a surprising level of particle activity and structural complexity. These observations indicate that the interstellar medium may not be an empty backdrop for cosmic motion, but a lively textured environment with its own systems of pressure, turbulence, and magnetism. This realization introduces an entirely new paradigm. Interstellar space is a fluid, almost atmospheric domain. Unlike the sharp transitions imagined between solar space and the galaxy beyond, Voyager 2 suggests there is instead a continuum, a kind of gradient zone where influences blend and compete. This fluidic interstellar medium seems capable of influencing spacecraft motion, distorting energy fields, and perhaps even affecting the propagation of signals, making future interstellar communication and navigation more complex than expected. Another layer to this is the behavior of charged particles, or cosmic rays, which continue to intrigue scientists. As Voyager 2 presses further into the interstellar void, it is recording cosmic ray intensities at unprecedented resolution. What's fascinating is that the behavior of these particles isn't as uniform as predicted. Rather than arriving in a smooth, even flux from all directions, cosmic rays appear to be influenced by localized magnetic domains, zones of varied intensity that seem to act as focusing lenses or deflectors. This has the dual implication of interstellar magnetic fields being both stronger and more turbulent than once assumed, and also of them having structures that persist over massive distances. This is not just academic curiosity. Understanding how these rays behave affects everything from spacecraft shielding to theories about the origin of high-energy particles. If interstellar space has weather in the form of particle storms or magnetic whirlpools, then spacecraft must be equipped not just to survive vacuum, but to adapt to a dynamic and sometimes chaotic energy landscape. It also challenges particle physics, pushing scientists to revisit the sources and life cycles of these high-speed visitors from the far reaches of the galaxy. The measurements have even hinted at interactions that mirror processes previously only observed in the Sun's corona or Earth's magnetosphere. Reconnection events, where magnetic field lines snap, rejoin, and release vast amounts of energy, may be occurring in this region of interstellar space as well. Such events would produce brief but intense bursts of energetic particles and radio emissions, exactly the kind of odd phenomena Voyager 2 is now beginning to detect. This brings into focus the possibility that energy in interstellar space is not passively drifting but actively being generated, shaped, and transformed. Furthermore, there is the concept of interstellar shockwaves, ripples caused by ancient supernova or the movement of stellar bodies through the galactic disk. Voyager 2 could be encountering the distant edges of one of these shockwaves, long since diluted but still capable of disturbing particle flows and magnetic arrangements. These residual tremors from stellar death events might persist for millions of years, continuing to propagate through the galaxy and subtly shaping everything in their path. The probe's readings, when cross-referenced with galactic maps and astrophysical data, may ultimately trace the echo of long-dead stars, leaving fingerprints in the interstellar medium itself. The very structure of the heliosphere, previously assumed to be comet-like with a rounded front and a long trailing tail, is now under intense scrutiny. Voyager 2's trajectory provides an alternate perspective from Voyager 1, and discrepancies in their findings suggest that the heliosphere might be more irregular and dynamic than a simple model can explain. Some new theories suggest a croissant-shaped heliosphere with two jets on either side, formed by the Sun's complex magnetic field interactions with the galactic magnetic field. If true, this means our solar system is being sculpted not just by what comes from within, but by persistent forces pressing from outside. This interstellar influence brings up critical questions about the long-term stability of the solar system's protective bubble. The heliosphere is our first line of defense against the majority of harmful galactic radiation. If the boundary can fluctuate or be distorted by outside pressure, then Earth's exposure to cosmic rays may vary over centuries or millennia, potentially influencing climate patterns or mutation rates in life. These cycles might align with known cosmic patterns, and Voyager 2 could be supplying the observational foundation needed to connect celestial mechanics with geological or biological history. What Voyager 2 is now doing also touches the fringe of one of the oldest and most profound scientific questions. How do stars interact across the galaxy? Are the magnetic fields of distant stars truly isolated from one another, or is there a vast tangled web of interstellar magnetism connecting them? If even a weak coupling exists, then the actions of one star, especially a supernova or flare, could have cascading effects, triggering magnetic waves that propagate across stellar neighborhoods. Voyager 2's data may be showing the earliest signs of such interconnectedness, where solar and galactic fields meet and mix in a fluid dance across light years. This opens the door to something even more extraordinary: the idea that there are zones of influence in the galaxy that are not defined by gravity alone, but by magnetic pressure and particle flows. Imagine regions in space where interstellar conditions are fundamentally different, not just due to proximity to stars or nebulae, but because of sustained electromagnetic structures. These regions could offer protection, pose threats, or even provide unique environments for chemistry or the formation of exotic matter. If such zones exist, and Voyager 2 has entered one, then this spacecraft is not merely exploring the space between stars. It is mapping the hidden geography of the galaxy. Consider also the subtle but increasingly persuasive argument that Voyager the 2nd of May be brushing against unknown fundamental forces or unrecognized interactions. For decades, theoretical physicists have speculated about deviations in gravity or the existence of scalar fields that permeate space. While Voyager 2 wasn't designed to test such theories, the anomalous acceleration behaviors of deep space probes have reignited interest in this domain. If the probe's motion or signal timing continues to deviate from expectations, it might offer empirical hints toward modifications of general relativity or quantum field theory that could reshape modern physics. Parallel to these grand physical implications, Voyager 2 is demonstrating something crucial about technology and engineering: longevity under adversity. Its instruments, while limited by today's standards, were so robustly designed and so meticulously crafted that they remain operational nearly 50 years after launch. This endurance is not just a triumph of engineering, it serves as a model for how humanity might build future interstellar probes. Modular systems, passive stabilization, minimal moving parts, and autonomous data handling. All these principles, proven by Voyager, will be vital for the next generation of explorers. The telemetry and data compression techniques used by Voyager 2 also highlight the necessity for innovative communication strategies. With such vast distances involved, signals take over 18 hours to reach Earth and travel at mere watts of power. Yet the Deep Space Network can still capture these whispers from the edge of the solar system. This pushes current communication models toward technologies like laser-based data transmission or quantum communication, ensuring that future missions will maintain connectivity across far greater spans of space and time. The psychological and philosophical dimensions of Voyager 2's voyage cannot be overlooked either. The probe, now in interstellar space, is a human artifact moving through a realm untouched by biology. It carries with it the Golden Record, a symbolic time capsule meant for any intelligent beings it might encounter, a message in a bottle drifting through a cosmic ocean. The knowledge that Voyager 2 is passing through unknown territory, broadcasting back not just measurements but metaphors of curiosity and perseverance, captures the enduring human urge to reach beyond the immediate horizon. Every signal that Voyager 2 sends is a ripple from a time when the Cold War still divided the world, when no planet had yet been visited by a rover, and when Earth's first steps into space had only just begun. And yet, that distant hum carries insights that may unlock future interstellar missions, inform the design of spacecraft that could one day visit exoplanets, or guide probes to pass between star systems using natural paths shaped by magnetic fields and plasma flows. Now that we have direct data on the characteristics of interstellar space, this new domain might be used not just for exploration, but for propulsion. Concepts like magnetic sail propulsion or plasma drag sails, long considered speculative, may now find their foundations in the plasma and field readings from Voyager 2. If spacecraft can anchor themselves to magnetic or plasma structures, they could surf these features with minimal energy expenditure, enabling long-duration missions that don't rely on traditional fuel. There's also the possibility of long-range sensing. If the interstellar medium propagates signals or disturbances efficiently, it might become a tool for passive observation. Spacecraft could detect distant stellar flares, massive gravitational events, or even planetary-scale electromagnetic signatures by reading the vibrations of interstellar space. Voyager 2, having passed through the dense plasma boundary and into the galactic medium, may already be experiencing such subtle signals, undetected by Earth-based telescopes. Looking further into the future, humanity may establish autonomous outposts in interstellar space, sentinel stations that float far beyond the heliosphere, monitoring galactic conditions, relaying communications, or even serving as launch points for missions to other stars. Voyager 2's experience lays the groundwork for this. It demonstrates how spacecraft can survive, operate, and send back critical data from a realm that was once thought utterly inaccessible. The legacy of Voyager 2 is being written in real time. Its discovery at the edge of the solar system was not just an anomaly, it was an invitation, an offer to rethink, to expand, to imagine. The probe's journey is a reminder that frontiers are never final. They are stages of transition, opening onto yet deeper mysteries. With every byte of data, Voyager 2 offers a profound message. The universe is richer, stranger, and more interconnected than any theory dared to assume. It is not merely charting new space, it is challenging the very definition of space. Not empty, not silent, not static, but full of texture, movement, energy, and secrets. And as it drifts ever deeper into that unlit domain, humanity listens, not just for answers, but for the sound of new questions being born. As Voyager 2 drifts ever deeper into the interstellar void, what continues to unfold is not simply the tale of a single spacecraft, but the unveiling of a transitional realm between solar influence and the broader galactic environment. This narrow band, once thought to be a thin and passive border, is proving to be a bustling region full of subtle complexities and previously unknown dynamics. As the probe sends back data from this uncharted expanse, it's allowing scientists to move beyond textbook models and into real-world observation, confronting the raw and often unpredictable conditions that define the outermost territories of our solar system. One of the most striking aspects of Voyager 2's current trajectory is the consistency and persistence of interstellar plasma phenomena. Although the density spike at the heliopause marked a dramatic transition, what lies beyond it is proving to be just as compelling. Unlike the heliosphere, where solar wind particles move outward in relatively consistent streams, the interstellar plasma appears to exhibit more irregular and chaotic motion. Voyager 2 is detecting layers of turbulence with eddies and currents on micro and macro scales. This layered nature suggests that plasma in interstellar space behaves more like an ocean with underlying currents than like a uniform gas. These layered plasma structures could influence the trajectory and behavior of interstellar objects. If regions of interstellar space have natural plasma corridors or zones of lower resistance, this might help explain how certain comets or rogue objects navigate interstellar distances before entering solar systems. The interstellar medium could be more of a guided terrain than a formless void, meaning future probes may one day use its natural flows for faster or more efficient travel. In tandem with plasma motion, temperature anomalies in interstellar space continue to puzzle researchers. The expectation was that once beyond the sun's influence, spacecraft would enter a thermally neutral environment where heat exchange would be minimal. Yet Voyager 2's instruments reveal localized thermal variations, pockets where particle activity generates surprising spikes in temperature. These warm zones could be driven by interstellar shock fronts or by interactions with relic radiation. Possibly even the cosmic microwave background being warped by concentrated magnetic regions. The source of these heating effects could also be tied to anisotropies, directional variations, in the interstellar medium. Anisotropic pressures might stem from the galactic magnetic field exerting force unevenly across space, creating pressure differentials that allow heat and charged particles to pool in certain directions. Voyager 2 is now moving through such a zone, effectively becoming the first probe to give us a cross-sectional view of this anisotropy. If galactic magnetic fields bend or compress the medium unevenly, this could provide new insight into the large-scale structure of the galaxy. This leads naturally into the concept of interstellar sound, vibrations traveling through plasma in the form of pressure waves or magnetoacoustic phenomena. These aren't sound waves as we know them, since they don't travel through air, but rather low-frequency oscillations carried by plasma density fluctuations. Voyager 2 has detected such waves, known as plasma oscillations, giving scientists their first opportunity to listen to the galaxy's ambient energy. These waveforms are valuable not only for mapping plasma density, but also for detecting long-distance interactions, perhaps even from events light years away. The spacecraft is thus not only a traveler but also a sensor, attuned to the subtle resonances of interstellar space. Interestingly, Voyager 2's slow drift also brings it into regions with variable interstellar dust content. Previously, dust was considered a minor component of interstellar matter, but current observations suggest it plays a more active role in shaping electromagnetic fields and particle behavior. As Voyager 2's instruments sweep through these areas, they record fluctuations in dust grain size, composition, and velocity. These particles may influence how cosmic rays propagate, acting as physical and electrostatic barriers or lenses. Furthermore, interstellar dust might provide insights into galactic chemical composition, carrying traces of past supernova, ancient stellar cores, and even prebiotic molecules formed in cold molecular clouds. These trace elements could have deep implications for our understanding of cosmic seeding, the process by which the building blocks of life are distributed across galaxies. If Voyager 2 continues to detect complex organic compounds embedded within interstellar dust, it could bolster theories of panspermia, where life's chemical precursors travel via space dust to planetary systems. These materials may survive for millions of years in dormant form, activating only when they interact with warm, chemically rich environments like young planetary atmospheres. Another frontier being quietly opened by Voyager 2 is the study of time-dependent phenomena in interstellar space. While most galactic processes are measured over massive timescales, the spacecraft's real-time data now enables the observation of short-term fluctuations. This includes temporary disturbances in particle flow, irregular wave bursts, and even transitory magnetic pulses that last only minutes or hours. Capturing these quick events adds a dynamic layer to the understanding of galactic processes, showing that the interstellar medium isn't just shaped by long epochs, but by continuous fleeting activity. Voyager 2 has also begun to observe directional asymmetry in interstellar radiation. The expectation had been that absent solar interference, cosmic radiation would be isotropic, equal in all directions. Yet, the probe records areas of increased particle flux arriving from specific galactic coordinates. These anisotropies might reflect nearby cosmic events such as pulsars, black hole jets, or large-scale star-forming regions that emit directional energy. Mapping these variations could allow scientists to backtrack high-energy particles to their origin points, offering an unprecedented glimpse into the galaxy's most energetic and violent processes. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Voyager 2's discovery? What do you think it means? We want to hear from you. Thank you for watching, and see you next time.